Hello everyone, very good evening to all of you. I hope I'm audible and visible. So let's wait for 5 to 10 minutes so that everyone can able to join the session. Okay, let's start the session. Hello everyone, my name is Pooja Verma. I am PMR Research Scholar from IIT Kharagpur and instructor for this course is Professor Shantanu Chattopadhyay, Electrical and Electronics Engineering Department, IIT Kharagpur. This is a week 9 live interactive session on digital circuits. You can use the chat box for asking and interacting. So these are the some topics which have been covered for this week. So I hope all of you have gone through this week video lectures. So the outline for this week content is the first one is semiconductor memories, memories, random access memories and sequential access memories, then error detection and correction in which they have discussed about Hamming code and read-only memories and combinational PLDs, programmable logic array and programmable array logic and some memories part also ROM, EPROM, double EPROM and in the last field programmable gate array FPGA have been discussed. Okay, so let's move to the questions for this week. So the first question for this week is a RAM is a option A is a non-volatile memory, option B is a volatile memory, option C is static and dynamic memory, and option D is volatile and either static or dynamic memory. So RAM stands for random access memory. Okay, it is a type of volatile memory. That means it loses its data when the power is turned off. Okay, if there is no power, then the stored data will be lost. Okay, and in that case, RAM has been categorized into two types. First one is a static RAM, and another one is a dynamic RAM. Okay, static RAMs are faster and more expensive used in a cache, while dynamic RAMs are slower but cheaper used to maintain used in the main memory of the most of the computers. Okay, so option D is the correct answer for this question. That is, it is a volatile and it can be either static or a dynamic. Okay. Okay. So moving to the next question. Next question is the density of a dynamic RAM is option A more than that of the static memory, option B less than that of the static RAM, or C equal to static RAM, or D equal to or more than that of the static RAM. Answer is already given. If you want, you can choose the answer and comment in the chat box so that in that case we can feel that this is an interactive session. So density of the dynamic RAM is more than that of the static RAM. The reason is as is given, the SRAM has a lower density due to complexity of the circuit needed to store data, more transistors per bit. Static RAM needs more transistors per bit, approximately 6 transistors per bit it requires. That meaning less memory can be stored in the same physical space, while dynamic RAM has a higher density since it only requires one transistor and one capacitor per bit. Okay, that allow larger memory size in a smaller area. So dynamic RAM has a higher density than static RAMs. Moving to the next one. So next question is also theoretical question. So it is given as which of the following memories can be programmed once by the user and then cannot be erased and reprogrammed. Option A is EPROM, option B is double EPROM, and then C ROM, and option D is PROM. So here the explanation for each option is given. So correct option 1 is D, ROM. Okay, programmable read-only memory. It can be programmed once by the user after manufacturing. Once it is programmed, it cannot be erased or reprogrammed. Okay, while EPROM is erasable, programmable read-only memory. It can be erased, but it uses exposure of UV light and it can be reprogrammed. While double EPROM, that is electrically erasable, programmable read-only memory, can be erased and reprogrammed electrically multiple times. It can be reprogrammed multiple times. And the difference between EPROM and double EPROM is it can be erased by the exposure of UV lights and it can be erased by electrically. Okay, and ROM stand for read-only memory. It's programmed during manufacturing and cannot be altered by the user. It is also cannot be erased and reprogrammed. Okay, so the correct option is ROM. Now next one is a numerical question. So a 12-bit Hamming code word containing 8 bits of data and 4 bits is read from memory. 4 parity bits is read from memory. Was the original 8-bit data word that was written into memory of the 12-bit word? Read out is here 12-bit Hamming code is given. That is this one. Now we need to find out the 8-bit original 8-bit data word. Here the 4-bit parity bits are also added. Okay. So 12-bit data is given as 1 0 1 1 1 1 1 and 6 times, yeah, 0 1 0 0. Okay. So as we know that already know that there is 8-bit data and 4 bits are parity bits. So parity bits are placed at which position? Already we know that power of 2. Okay. At the power of 2, the parity bits are placed. Yeah, power of 2, the parity bits are placed. So the positions of the parity bit are parity bit are 1, 2, 4, 8. Okay. So in the 12-bit sequence, so this one is the first 1, 2, 3, 4, 5, 6, 7, 8. So in these positions, parity bits are placed. Okay. So we can remove that, then we will get our data bits. Okay. So at these positions, parity bits are placed. So now we can take our, I'm writing it here, 0, 1, 0, 0. So P1, P2, P4, we can write D3 data points. That means D5, D6, D7. Here at 8 position, parity bit is there, so we can write it P8, D9, D10, D11 and D12. Okay, so remove these places, then we will find out data points. That is 1, 1, 1, 1, 0, 1, 0, 0. Right? So this is our data base. So choose from the options which one is correct. Yeah, correct. So option B is the correct option for this question. Okay, 4 times 1, then 0 1 0 0. Okay, so moving. I hope all of you have understand this question. Already. Yeah, yeah. What are you saying? Hello.
1, 2, 3 positions will start from MS-DO, no?
Your voice is little bit noisy, so I'm not able to. Yeah, what are you saying? Whatever you want to ask, you can use chat box also. Okay, you have any doubt? Okay, you can ask in the chat box. Actually, I'm not able to understand whatever you have asked. Okay, so I'm moving to the positions of the numbers, cat, MSB or LSB. Okay, so most of the time while we are using the Hamming code word, so we are taking from this side, just a minute, from this side, but if in the question it is written from this side, you can take it. But most of the time it is written in this side only. Okay, while we are solving the Hamming code related problems. Okay, many of the questions have been written from this side. One question I have like that. So if it is specified, then it is okay. Otherwise, most of the time we will take from this side only. Okay, while we are writing, because it is
Okay, ma'am.
okay. So moving to the next question. The next question is how many parity check bits must be included with the data word to achieve single error correction and double error detection when the data word contains 32 bits. Here it is written the data word contains 32 bits. So how many parity check bits are included? How many parity check bits are needed to achieve for single error correction and double error detection? Okay. So for checking, please show both questions. Okay. Yeah. Yeah.
Okay, ma'am.
Okay. Okay. So here, in order to find out the number of parity check bits in the data point, for the number of data points are given, the equation is like this: 2 to the power k minus 1 is greater than equal to n plus k. Okay, this one is n. So where here I am taking n is the data bits and k is the parity bit. Okay, so here data bits are given here, that is 22, n is equal to 32, sorry, 32 is given. Okay, now we need to find out the k. So we have to power k minus 1 equal to 32 is given, 32 plus k. Now in order to find out or k, the number of how many parity check bits, we have to put the value of k which is that part is greater than to this part. Now we have to put the different values of k and check it. Then whatever value of k this condition will satisfy, then that value we need to take. Okay, so for example I am taking for let's for k is equal to 1, what will be, what it will come? So 2 to the power 1 minus 1, that is 32 plus 1. So it will come 1 only. So it is, that condition is not satisfied, right? Then similarly check for k is equal to 2. So here it is 2 to the power 2 minus 1, that is 32 plus 2. So here also condition is not satisfied. We need to check it. Most probably we can assume here that for k is equal to 6, it will work. Okay. So 2 to the power 6 minus 1 is greater than 32 plus 6. So how much it will come? 64 minus 1, that is 63, is greater than equal to 38. So for k is equal to 6, if the condition will be satisfied. You can check for k is equal to 5 also. So 2 to the power 5 minus 1 is 32 plus 5. So it, here it will come only 31. So that condition also will not satisfy. So for k is equal to 6, the condition will be satisfied. So for k is equal to 6, the condition will be satisfied, but it is used only single single bit error correction and single bit error detection. For double single error correction and double error detection, we need to add, for double error detection, we need to add 1 in parity with. Okay. So here k plus 1 for double error detection. Okay. So have you understand? Yeah, correct. For whatever value of k comes, that is used for only single error correction and single error detection. For double single error correction and double error detection, for this case, we need to add 1 in that parity weight. So that means k plus 1, that is 7. Okay. 6 is only for single error correction and single error detection, not for double error detection. For double error detection, we need to add, check this point. Here it is written single data to achieve single error correction and double error detection. So for double error detection, we need to add one extra parity weight for double error correction. Okay, so that's why we have added in 6, that we have got number of parity weights that is used for single error correction and single error detection. For double error detection, we need to add one more parity weight in the parity. So that is k plus 1, 7. 7 is the correct answer. Okay. For double error. So this option D is the correct one. For double error detection. For double error detection, we need to add one extra parity bit. That is 7. This one is the correct answer. Option D is the correct one. Okay. Okay. So I hope you have understand this question. So moving to the next question. Okay. So next question is also from Hamming code only. So here, given the 8-bit data words, that is 0101, 1011, generate the 13-bit composite word for the Hamming code that corrects single error and detects double error. Here also we need to detect double error and correct up to single error. Okay, so here the data bit is given, that is data bit is given, it is 0 1 1 0 1 1. Here 8-bit data is given. So how many parity bits we can add in that data? Any one of you can answer this question? Yeah, but in that case it is only 12. So if we add only 4 parity bits, in that case that only correct single error and also detect only single error. For double error correction, we need to add 5. Okay, so first we will see that how many parity bits we need to add in that case. First we need to check in that equation. So how we get the how many parity bits we need to add into data bits. So already we know that formula. In order to find out the number of parity bits we need to add, that is 2 to the power k minus 1 greater than equal to n plus k, where already we know that n is the data point and k is the parity bits, right? It is the parity bits and n is the data bits. So here data bits is given, that is 8, 2 to the power k minus 1, that is greater than equal to 8 plus k. In the same way, we need to find out by putting the values of k and then find out the whatever the equation that condition is satisfied, then that is the number of. So for k is equal to 4, the equation will be that relation will be satisfied, that is 2 to the power 4 minus 1, 8 plus 4, that is 16 minus 1 greater than 12, right? It is a 15. So for k is equal to 4, the condition is satisfied. So here already we know that we can add the 4 number of parity bits in that data bit. But here we need to detect the double error. So in that we need to add one extra parity bit in the existing parity bit. So 4 plus 1 is equal to 5 for double error detection. Okay, and single error correction. Okay, so already we know that how many parity bits we need to add in that case. So total 5 parity bits we need to add. So total how many? 8 are the data bits and 5 are the parity bits, that we will get 13-bit composite word. Okay, here already it is satisfied, we need to make a 13-bit composite bit. Okay, that's how we will get the 13-bit composite. So I need to remove this in order to solve the further questions. Okay, so already we have seen that how we will get the number of parity bits that we need to add. Okay, so total. So let's start from the bit positions. So it will be easier. So already we know that where we need to place the parity bits, power of 2. Power of 2. That is 1, 2, 4, 8. Okay, now next one is 16. So that will not exist. Okay, so at in the last parity bits we will add positions of parity bits. Okay, so I can take it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so at first position there is one parity bit, and second position it is also parity bit, and at the third position there is a data bit, fourth position one parity bit, that is P4, and fifth position of the data bit, that is D5, D6, D7, P8. Okay, there is one parity bit at 8. So D9, D10, D11, D12. So all data bits and parity bits have been completed. So one extra parity bit which we have added, so that we will place here, that is P13. Okay, so now in the data bits already given, so we can place in the places of data bits. So that is 0, here 1, 0, 1, right? 1, 0, 1, 1. Now we need to find out the parity bits. Okay, so how we can find out the parity bits? So in order to find out these parity bits, the values of this parity bit, we need to use the data bits. So at the position P1, for the position P1, we need to take XOR of the data bit positions. So for P1, we have to take one. We have to take this one, then leave one place, then take this one, then after removing one places. Okay, so D3, then D5, D3, then if in between this, if there is any parity bit, so we have to leave that one. Okay, so D3, D5, then D7, D9, D11. So D13 is the parity bit, so we cannot take this one. Okay, so for P1, so XOR of 0, D3, then D5 is 1, then XOR of D7, that is also 1, then XOR of D9, that is also 1, and then XOR of D11, right? That is 1. So what will be the value that will come? 0 XOR 1, that is 1, 1 XOR 1 is 0, 0 XOR 1 is 1, then 1 XOR 1 is 0, right? So P1 will come 0. Okay, so yeah, are you getting this? Okay, so similarly we need to find out the P2. Okay, so P2, how we will get that? XOR of the positions. So P2 is stands for here, right? So first we need to take D3. Then next one is P4. So we cannot take this one, right? So now D3, after D3 we have to do two positions. Here the gap between the bits which have been taken is two positions. Okay, so D4 and D5 will be removed. Then D6, D7. Okay, then remove two positions, then take D10, D11. Then we have to also not take the two positions. Take two positions, then leave two positions. Okay. So D3, value of D3 is 0, 0 XOR, that is D6 is also 0, then XOR D7 is 1, then XOR D10, D11, that is 0, then XOR 11 is 1. So again, if you take XOR, then you will get 0, because 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 0 XOR, sorry, 1 XOR 1 is 0, okay. Or you can check directly the number of ones. If number of ones are even, then it is 0. If it is odd, then the value will be 1, okay. So now we have got the P1 and P2. Similarly, we need to find out the P4 and P8. Okay, for that, where I can remove, so I can remove, okay, I am writing it here. P1 is equal to 0, P2 is equal to also 0. Now we need to find out the value of, so I am removing from here so that we can write it. Yeah, P4 is 1, you are correct on me too, but I need to solve it also. Okay, so I remove it from here also. So now we need to find out the P4. So P4, can anyone of answer in the chat box at which position we need to XOR for P4? XOR of positions. P4 is here, so we have to take in this forward. The next one is what is this? So P4 is D5, D6, right? Then D5, D6, comma D7. We have to take here 3 positions. Then leave for 3 positions. Okay. Then one will, that 3 will be leave. Then after 3 we have to take at which position? D12, right? After that there is a one parity bit, so we cannot take forward. So D5 is 1, then D6 is 0, D7 is 1, and D12 is 1. So here odd number of ones, so directly we can write it 1. Otherwise you can XOR it. 1 XOR 0 is 1, 1 XOR 1 is 0, then 0 XOR 1 is 1. So P4 will come as 1. Now next one is P8. So for P8, which positions we need to XOR? Yeah. For P8, it is XOR of P8 is here. So after that we need to take, so that is D9, D10. Here we have to take 4 positions, then leave for the next 4 positions. D9, D10, D11, D12. Okay, now next one is P13, so we cannot take. Okay, okay, so D9 is 1, then D10 is 0, then XOR of 1, XOR of 1. So there is odd number of ones, so directly we can write it as a 1. So already we know that we have got P1, P2, P4 and P8. So how we can find out the P13? Now put the values in this sequence. So in that case we can able to find out. Okay, so I can remove from here. So P1 we have already got 0, P2 is also 0, P4 we have got is 1, and P8 is also 1. Okay, so now I'm removing all these things from here so that we can write. Okay, so P1, P2 are 0, 0, P4 is 1, P8 is 1. Now what we need to do? We need to check this series. Okay, the number of ones in the series. If number of ones are even, then we need to add 0 in the place of P13. If it is odd, then we need to add 1 in that place. Okay, so now sequence that we have got, that is 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1. Now P13 is left, so now we need to check the number of ones in this series. If number of ones are even, then we have to put the value P13 is even. If it is number of ones are odd, so we need to add 1 for P13. Okay, so number of ones are 1, 2, 3, 4, 5, 6, 7. So total number of ones are 7. Number of ones equal to 7. So it is odd. So value of P13 will be 1 only. Okay, so that is 1. So overall sequence we will get, that is 1, this one. Okay, so have you understand this question? Have you understand this question? So value of P13 is 1. So overall we got this sequence. Now we need to check in the options which option is correct. So if you match that, you will get the option B is the correct one. That is 0001, then 1011, then again 1011, then final one is 1. Okay? Yeah, me too. Correct. Option B is the correct answer for this question. Okay? Okay. So option B is the correct option. And this one is a 13-bit composite word. The 13-bit composite word for the Hamming code is this one. Okay. Okay. So I hope all of you understand this question. So moving the next question. Okay. Okay. So next question is the memory unit that follow are specified by the number of words times the number of bits per word. Okay. So how many address lines and input output data lines are needed respectively for 16 capital of M multiplied by 32? Okay. So how many address lines and input output data lines are needed? Okay. So the question, the memory units that follow are specified by the number of words times the number of bits. That means this one is the number of bits and the number of words that is stored in that place. Okay, so we can say that the address line that is address lines are denoted by A, and data lines, that is input output data lines, are denoted by D. Here let's, okay, so already we know that the how we can represent the address lines and data lines, that is 2 to the power A into D, right? Here it is a number of data lines and this one is a address lines total. So now we have to put in that format. Okay, so given is that is 16 m into 32. 32 means that is data lines. Okay, this one is the data lines. Already we got the number of data lines. Now we need to find out the number of address lines. So 16 in m is for in memory unit, m is represented by 2 to the power 20. Okay, yeah, the representation of m in memory units or binary is represented by 2 to the power 20. So put here that is 2 to the power 20 into 32. 32 is the data lines, already we know that. And how we can represent that 16? 16 is also represented by 2 to the power 4, right? Into 2 to the power 20. And these are in the multiplication, we directly add this, that is 2 to the power 24 into 32 bits, right? So we have got in this format 2 to the, so A is the 24 and D is equal to 32. Okay, so we have got the number of address lines and number of data lines. Okay, so A is equal to 24 and D is equal to 32. Okay, so option C is the correct answer for this question. Okay, so I hope you have understand this, how to solve this type of question. So now moving to the next question. Okay, just a minute. क्लास चल रही है ऑनलाइन, आपको मैसेज कर लो ना, क्लास मुझे कॉल कर लेना। हाँ हाँ, कुछ इम्पोर्टेंट है? हाँ हाँ, कुछ मैडम का कॉल आया था इसलिए। अरे वो बहुत क्लास में लीव है। हाँ हाँ, मुझे कॉल कर लेना लेकिन। हाँ हाँ हाँ। Sorry for the disturbance. Yeah, capital M will be 2 to the power 20 in the memory unit. Okay. And where capital K is represented as a 2 to the power 10. Okay. If here somewhere it is given. Okay, yeah, sorry. Now I am audible. Yeah, okay. So M is always, M is represented in terms of memory unit is 2 to the power 20. If K is written here, so it is a 2 to the power 10. Okay. Okay. So I hope now you have understand it. So moving to the next question. So next question is, for the given circuit, which of the following is correct? For this circuit, which option is correct? Okay. So here we can see that this is a address lines are given, that is 7. Okay, and their values are also given. So from there we can find out the what will be the at which location it is written. Okay, these are the number of data inputs, which whatever data we have given, that will be input from here. And here the whether it is enabled or not, here the read write operation, whether it is reading or writing. Okay, and here it is a corresponding data outputs. Okay, so options are given. The number 5 is being written to the memory at address location 203. Now first we need to find out what will be the address location. How we can find it out? So first we need to check the address inputs. What are the address inputs? That is address inputs. So address inputs we can write A7, A6. Here it is already given. A5, A4, A3, A2, A1 and A0. So what are the values? 1, 1, 0, 1, 0, 0, 1, 1. Okay. So it is given in the binary. We can directly convert it into a decimal because it is written in the decimal. Okay. So what will be the value of this? In the decimal 11010011. If you convert it, what will value we will get? Anyone of you want to answer this question? What is the decimal conversion of this binary bit so that we can get the address input? What will be the value? So what we will get if you convert it? Yeah, it is 211. If you convert it, we will get 211. So how we can convert it? Already we know that 2 to the power 0, 1, 2 to the power 2, power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. Okay, then we will get 128 plus 64 plus 16 plus 2 plus 1. We will get it 211 in decimal. Okay. So address location will be 211. Okay. So that will be incorrect. Now we need to check also data point. For data point, what will be the corresponding decimal value for the data points? Okay. Here it is written D3, D2, D1, D0. Okay. It is written 1, 0, 1, 0. So it is already we know that 8 to 10. The decimal conversion of the 10. So address will be the data input is 10. Yeah. Address location is 211 and the data which are written is 10. Okay, now we need to check whether it is a read operation or write operation. So here the input is given 0. So 0 if it is directly goes in, that means read. But here the 0, that means not readed anything. Here write, that will be the 1. If yeah, it is write operation because this dash is there. Okay, so dash will be 1. If it is 1, here it is given as a 1, so that means it is read operation, but here it is given as a 0. 0 means 0 dash, that means 1. In that case, that means write operation will be performed. Okay, so now choose from the options. The option A is the number 5 is being written to the memory at the location 203. No, address location is not 203. It is, we have solved, that is 211. So that is incorrect option. Now the chip has not been enabled since enabled terminal is 0. Okay, here it is 0, but it is enabled dash. So that will be the 1. So that one is also incorrect. So therefore nothing will be the written to the chip and the output is the tri-stated. Now next one is C. decimal 10 is being written into memory location 211. That is the correct. That memory location is 211 and decimal value is 10 and the operation is right. Already we have seen that. Okay. So that this one is the correct option. Decimal 10 is being written into the memory location 211. So here the fourth option is the read or write of line is low. Therefore, decimal 5 is being stored at memory location 211. But the decimal value is 10. We have seen that. So this one is also correct. This one is incorrect. So option C is the only correct option for this question. Okay. Okay. So moving to the next question. Now next question is how many address and data lines is there in 1M into 16 ROM system? So how many address lines and data lines will be there? So already told you 2 to the power A into D, where D is the data lines, A is the address line. Now we have to put in this way 1M into 10 to the 16. Yeah, 20 into 16. That is correct. So already M means we know that 2 to the power 20. So that means 1 into 2 to the power 20 into 16. That means 16 is the data lines. Already we know that. And if we write it is a 2 to the power 20 into 16. So this is the data line and this one is the address line. So address lines are 20 equal to 20 and data lines is equal to 16. Yeah. So option B is the correct answer for this question. Okay. So moving to the next question. So now next question is a theoretical one. So which of the following statements is false? Okay. So it is given as option A is in SRAM, information in the memory gets lost as soon as power is switched off. Okay. So already we have seen in the previous question also SRAM is the volatile type memory. So when the power is gone, then content of the memory will be lost. Okay. So this one is the correct. So now next one is the content. The content of a memory in DRAM needs to be periodically refreshed to prevent data loss. That one is also correct because DRAM has been made by transistor and one capacitor, right? One transistor and one capacitor. So capacitor continuously needs a refreshment. Okay. So DRAM is periodically refreshed to prevent the data loss, whatever is stored in the DRAM. So that option is also correct. Now next one is option D is also correct because SRAM and DRAM are both volatile memories. Already we have seen that. Now next option C is the access time of the sequential memory is constant independent of the position of the word. Here it is given independent of the position of the word. So this statement is false and the related the related content is given below. So it is given the access time of the sequential memory is constant independent of the position of the word. That is refers to a situation where the time to access data from the memory remains same regardless of the location of the data in that memory. Okay. So this statement is false for the sequential memory. Okay. For the sequential memory, the data has been accessed in the specific ordered sequence. To retrieve a particular piece of information, the system might need to be scanned through the memory locations in order. That means access time is not a constant because it depends on the position of the words being accessed. Okay, it is a position of the accessed. It is dependent on the position of the words being accessed. The closer the data word is starting point, the faster it can be retrieved. Okay, and conversely, the farther it is, takes longer time to access it. And consequently, in random access memory such as SRAM and DRAM, the access time is constant because data can be retrieved directly from any location, irrespective of its position. That's why it is called a random access. Okay, so for the sequential memory, the access time depends on the position of the word, not independent. It is a dependent of the position of the word. Here it is written independent. That's why option C is the statement is false. This statement is false. Okay. Okay. Moving. I hope you have understanding that previous one. The detail, yeah, file correct one. A detailed description is given. So now moving to the next question. So next question is, what function is implemented at output Q of the following PL circuit? Okay, what function we can implement here only at Q? What function is implemented at output Q of the following PL structure? Okay, so now we need to check the corresponding line. Okay, it is this one. So this one, this one, this one, this one. So Q is equal to, now we need to check here is a fixed OR gate. It is an programmable AND gate. Okay, it is fixed where it is a cross, that means that is a programmable. So now we need to check the first AND gate. Yeah, D is correct one, but how we can get it? So check from the corresponding this dot. So this is a B and the C dice. B C dice, the output of the first AND gate. That is B C dash. Now this one is A dash, B dash, C dash, D. That means that will be cancelled out. Similarly for next three NAND gates, so plus 0 plus 0 plus 0. So only we will get B C dash. Q is equal to. Okay. So that means option D is the correct answer for this question. Okay. Yeah. Option D is the correct one. Now moving to the next question. So next question is, how many 4 input LUTs? LUT stand for lookup table. Okay, lookup table would be required in an FPGA to implement the function y is equal to AB plus C dash. Y is equal to AB plus C dash. How many 4 input LUTs? मतलब 4 input LUTs. That means lookup table. So 4 input means 4 inputs are there and one 4 input lookup table is a lookup table with 4 inputs. Basically, it is a circuit that can implement any 4 inputs and one output function. Okay. So here the y is equal to AB plus C dash is given. So how many variables are there? So 1, 2, 3. 3 variables are there. Okay. Only 3 inputs are involved. 3 inputs are there, but we can implement the 4 inputs. So how many lookup tables are required? So that can we implement only one lookup table, because that for one lookup table we required 4 inputs, but here 3 inputs are there only. So we can make the 3 inputs by the 4 input lookup tables. So that can we require only one LUT. Okay, 4 input. We can say that 4 input, only one 4 input lookup table we require. Here it is. Only one 4 input lookup table are required. Okay. So option A is the correct answer for this question. Not able to see screen. Now is it visible? Uh, okay. From my side, it does not have any problem. I think it is clear to all of you. Okay, okay, it's visible. Okay, so now moving to the next question. So next question
And
is,
if it is a,
yeah,
if it have 5 variables, then 2 lookup tables are required.
5 variables. Yeah, in that case, 2 lookup tables are required. If there is a,
If it
uh,
is
it is
if it is
different type
9,
lookup
then
tables are also different types. Whether it is 6 input or 8 inputs, lookup tables are also available. So if it is
okay.
in the question, it is given the 4 input lookup tables are how many 4 input. So in that case, if there are 2 lookup tables are required. If there is a 5 input. Okay. Okay. So moving to the next question. So next question is the number of ACT1, that is Act1, FPGA logic blocks needed to realize the 4 input logic function, that is ABCD. If it is a coding, then 4 are required. Yeah, if it is a 14 inputs, yeah, 14 inputs or 14 variables are there, then in that case, why, yeah, 4 lookup tables are required. Yeah, you can calculate it based on that. One lookup table can solve the problem of 4 input variables. Okay. So now next one is the number of Act 1 FPGA logic blocks needed to realize the 4 input logic function, that is ABCD. The logic function is given is, so the number of FPGA logic blocks are needed. So first we will see what is the Act 1 FPGA logic block. So Act 1 FPGA logic block. So first to the first generation field programmable gate array developed by Actel. The FPGA architecture in the series Act 1 series is based on a logic blocks that can be programmed to implement a combinational logic function. Okay, this is also logic block that can be used or can be used to program or implement the combinational logic function. Okay, so here it is given f is equal to a b c d is equal to summation 0 1 2 5 8 9 10 13. So how we can we will able to find out the logic expression? So already we know that by using the K-map. So anyone of you want to solve this, the K-map problem, in order to find out the logic or Boolean expression logic function, and let me know what will be the logic function for this ABCD of that one. So anyone of you want to solve this question? How to solve this one? What will be the logic expression for this one? Yeah, anyone of you answer it? B bar C and C bar D. Yeah, correct. Yeah, yeah, correct one. So here it is a 0 0. So 0 0 0 1. So we will move in this direction. So 0 at this place 1, then 1 1 0 1 2 3, then 4 5 6 7, then 8 9 10 11 12 13. Right? So there is a 1 chord will be there. So what will be the value of this one? That is C dash D. Right? Now we can make one chord here also. That is all the corner. So what will be the value of this one? This one will be the here 0 will be common, so B dash, and in that case T dash. Okay, the logic expression for F is equal to A B C D, that is B dash D dash plus C dash D. So now in this logic expression, how many variables are there? C, B, D, that is 3 variables, right? 3 inputs are there. Are there 3 variables? So the number of Act 1 FPGA logic blocks are built by also by lookup table only. Okay. In Act 1 FPGA implementation, each logic block contains a lookup table. Okay, that can be implement a function of 4 variables or 3 variables. So here also only one lookup table or 4 input lookup table or Act 1 FPGA logic blocks are required. Okay, because here if you solve this one, only 3 variables we are getting. So for 3 inputs or 3 variable problem, we can solve by only one Act 1 FPGA logic block. That is the only lookup table. Okay, that use a lookup table to implement any logic function. Act 1 FPGA logic block use the lookup table to implement any function. So here 3 inputs are there, so only one Act 1 FPGA logic block, or you can say that lookup table are required to implement this function. So here only one Act 1 FPGA logic block are needed. Are needed. Okay, so option B is the correct answer for this question. Okay. Okay, so I hope all of you understand this question. Okay, so moving to the next question. The next question is between coarse and fine grained FPGA block. So options are given. A is coarse grained ones required more area. Option B is coarse grained ones can accommodate more logic, or option C is coarse grained ones have more average find out, or option D is all other options are valid. So here first we can see that what is a coarse grained FPGA block and fine grained FPGA block. So coarse grained FPGA blocks are implemented by combinational functions with greater storage capacity or capabilities, while the fine-grained FPGA blocks can only implement a few logic gate simple configurable cell arrangements. Okay, so the coarse-grained FPGA blocks are implement any combinational function that can use mux, decoder, encoder, anything. But in a fine-grained FPGA block, we use only few logic gates and it has a simple configuration. Okay, so coarse-grained blocks typically reduce the number of individual configurable logic block, that is called as CLB, needed by packaging more functionality into each block. That and but potentially it reduces the overall area. Okay, and many smaller fine grained blocks are into the coarse grain blocks will be there. Okay, so coarse grain ones require more area, that can be required, and coarse grain ones are accommodate more logic blocks. Okay, that can accommodate the more logic blocks because it consider the all combinational logic functions, decoder, encoder, and for example, if we use fine grain, so for one decoder and encoder, there is also a lot of gates are required because it's made by simple logic gates. So that cannot able to accommodate more logic blocks, fine grained ones. Okay. So in comparison to that also the coarse grained ones have more average fan out. That can be a more average fan out means number of outputs. That can be a more number of outputs. So here option D is the correct option. All other options are valid for this one. Because coarse grained FPGA blocks can implement all combinational logic functions. Okay. You can read it in details. So now in that case you will find it out. Okay. Now next one is what minimum size ROM is required to implement an unsigned 4-bit binary adder. Okay. So anyone of you want to answer this question? So what the minimum size ROM is required to implement the unsigned 4-bit binary adder? Here the 4-bit binary adder is given. Okay. 4-bit binary adder. Okay, that means the minimum size of ROM is required. So in the ROM already we know that we cannot write. So to implement 4-bit binary adder, we need to store all the possible combinations because after that we cannot write. We have to write at once only. So for 4-bit, so there are two 4 bits are required to add. Okay, there is a 1 4, that means 2 to the power 4. There are two numbers that we need to add. So that each of these are the 4 bits. Okay, that means 0 1 0 0 1 0 0 0 like this, 4 bits. So total what minimum size of ROM is required to implement. So size will be the 2 to the power 4 for one, for that sequence to another number there is also 2 to the power 4, right? And for that 4 bit there is, if we add two 4 bits like that, so there are one carry out will be there, we have to store for that only, for one carry out, because there are 4 sums and one carry out, right? So that means there are 5 outputs are there. Here that means total possible combination from 0, 0, 0, 0 to 0, 1, 1, 1, 1. That is required. We need to store all possible combinations because whatever combination will be there, we have to take the memory size for that, because after that we cannot write. It is a ROM. So for that, for all possible combinations, we have to take like this. Okay. So these are the inputs combinations, and that one is the output. Okay. So 2 to the power 4, 2 to the power 4, already we know that this is 16 into 16 into 5, right? So 16 into 16, if we multiply that, is 256 possible size will be there into 5. 5 for output and this one is for input. Okay. So option B is the correct answer for this question. Have you understand this question? Okay. We need to add two 4-bit binary numbers. We cannot, there is written to implement an unsigned 4-bit binary adder. So for binary adder, we require two 4 bits. So this one is for one sequence and this one is for another sequence. Okay. So have you understand this one, this location, these are the locations for the first bit, and this one is for the another sequence that we have to add, and this one is the total output locations. We have to, for addition we require 2 bits now, so 4 bits we have to add. So these are the all possible.
Okay, ma'am.
Okay. Okay, so moving to the next question. So now next question is, I was talking about this question, is that we can write from this side and this side. If in that question it is written from this side, okay, from this side. So assume that a 12-bit having code word consisting 8-bit data and 4 check bits is, that is D8, D7, D6, D5, C8, D4, D3, D2, C4, D1, D2, C1. Well, the data bits and check bits are given in the following table. The data bits are given and that parity check bits are given. Now, which one of the following choices gives the correct value of x and y? Now, we need to find out the corresponding data bit and this one parity bit. Okay. So now it is written from this side. So we have to write it like this one also. So D8, D7, D6, D5, C8, D4, D3, D2, C4, D1, C2, C1. Okay, so D8 is given 1, 1, 0, X. Okay, that is D5 is X. Now C8 is Y, D4 is 0, D3 is 1, D2 is 0. Now C4 is also 0, C2, C1 is C2 1, C0 is D1 is 1. Okay, now we need to find out the x and y. How we can find it out? In the same way, from where we need to find out the P1, C1, C2, C4 and C8. Okay, that already we know that C1 is equal to XOR of the positions. At which positions? Anyone of you answer this question? Positions of D1, D2, D4, D5 and D7. Okay, you can check it. So D1 is 1 XOR, D2 is 0 XOR, then D4 is 0 XOR. Here X is given D5 because at the place of X, D7 is 1. So number of ones are even. So 0 XOR X. So how we can find out X? So for even parity already we know that even parity we have to take, for even parity we have to take X is equal to 0. If we take X is equal to 1, then that will be the odd parities. Okay, here we have assumed that X is equal to 0 for even parity. If it is 1, then we have to take 1 here. Okay, now similarly we have to find out the value of C2. So C2 is the XOR of what are the, that is D1, D3, D4, D6 and D7. So D1, D3, that is 1 XOR 1 XOR D4 is 0 XOR D6, that is 0 and XOR of D7, right, that is 1. So here the number of ones are odd, so 1. So C2 already we know that it is given 1. Okay, that one is correct because already it is coming to 1. Now check for C4 also, you will get 0. So XOR of at its position D2, D3, D4, D8, D2, D3, D4, D8. Okay, the if you XOR it, the number of ones are even, so you will get a 0. Now again we need to find out C8. We are interested to find out the C8. So for C8, what are the XOR of D5, D6, D7, D8 at the bit position. So D5 is X XOR D6 is 0 XOR D7 is 1 XOR D8 is 1. So already we know that we have assumed that X is equal to 0. So 0 XOR 0 XOR 1 XOR 1. So it is a even. So Y is also equal to 0. That means C8 means Y, right? So Y will be also will be 0. So that means X is equal to 0 and Y is equal to 0 we have got. So which option? Option 4 is the correct answer for this question. X is 0 and Y is 0. Okay. We have to just simply, we have to write it down and then find out the parity check bits. C1, C2, C4, C2, C4 and C1 is already given. Just we need to put these values in this and find out X and Y. Okay.
Ma'am, have you get this X value?
Yeah. X is equal to 0, right? That is here. If here we will put, just a minute. If we put X is equal to 1 here, then we will get the odd parity. So we cannot put here, for even parity we have to take X is equal to 0 here. Okay. Otherwise you can put the value of C1 is here. We have got C1 is equal to 0 XOR X, right here. So if C1 is given, so 0 is equal to 0 XOR X. So in order to find out the value of X, 0 XOR 0, we will get 0 only.
Okay.
Okay. So X is equal to 0 and Y is equal to 0 for that. Now moving to the next question. So next question is also related to Hamming code only. Same. So the final code after encoding data bits 1101 into a 7-bit even parity Hamming code. Okay, here it is given even parity. So already we know that how many parity bits we need to add. So data bits are 1101. So how many parity bits we need to add here? Yeah, 3 parity bits we need to add. So already told you how we will get that number of parity bits we need to add. 2 to the power k minus 1 is greater than n plus k. Okay, so here k is the parity bits and n is the data bits. So 2 to the power k minus 1 is greater than data bits are 4, 4 plus k. So if we put k is equal to 3, then that condition will be satisfied. So that is 2 to the power 3 minus 1 is greater than equal to 7. So that means 7 is equal to 7. So that condition will be satisfied. So here k is equal to 3. That means we need to add the 3 parity bits. Now we have to write in the same way P1, P2. Already we know that parity bits are added in the power of 2 positions of parity bit. Parity bit is 1, 2, 4, 8 power of 2. So here I am writing it here also. P1, P2, then data point 1 is D3, then P4, D5, D6, D7, right? That means data points. There are 4 data points. Already it is given. That is 1, 1, 0, 1. Data points are given. Now we need to find out the parity bit. So that can we find out from the data bits. Already we know that is P1 is equal to XOR of P1 XOR of what? We cannot take the parity bits. So that is D3. Then leave 1, D5. That is D3, D5. Then D7. Right? So XOR this 1 XOR 1 XOR 1. So it is an odd number of ones. So P1 is equal to 1. Similarly, we need to find out P2, that is XOR of D3, right? Then D5, D6 or D6, D7. That is D6, D7 because we need to leave 2 places. So now first one is D3. So 1 XOR I am writing it here directly. I am not writing this step. So now you can understand this one. So 1 XOR 0 XOR 1, right? The number of ones are even. So P2 is equal to 0. Okay, so P1 we have got 1, P2 we have got 0. Now similarly we need to find out the P3. So P3 is the XOR of P3 means that is P4. XOR of we have to take the 3 positions. So these are the 3 positions. 1 XOR 0 XOR 1. So it is also number of ones are even. So it will be 0. Okay. So these are the 7-bit even parity Hamming code. The number of ones are even here. So this is a 7-bit even parity Hamming code. Okay. So 1 0 1 0 1 0 1. So check from the options. So option 3 is the correct answer. Okay, for this question. 1 0 1 0 1 0 1. Okay. Okay, so I hope you have understand this question. So moving to the next question. So next question is it is given again. So Octal Corporation manufactures an FPGA family called Act 1. Okay, which has a multiplexer based logic block illustrated in figure P6.1. So how the function, this function can be implemented using only the act1 logic block. Okay, how we can implement this function? By using this logic block. So logic function is given as w2 w3 dash plus w1 w3 plus w2 dash w3, right? So w2 w3 dash plus we can take w3 common, right? So w3, so here w1 plus w2 dash. Okay, so this function we have to implement using this logic block, FPGA act1 logic block. So what inputs we have to give in this I1, I2, I3 in these places, so that we will get this function. Okay, so here these are the multiplexers. Okay, so these are the 0, 1. If 0 is there, so it will select this line, output will be passed to this one, 0, 1. Okay, for I6 lesson. So already I have solved it by taking the different combinations. So here it is a OR gate, right? So if we take, we will give W3 here and 0 here. So the output of this is W3, right? W3. If we give W2 here, 0 here, 1 here. So what will be the output here? W2 dash, but it is 0 and W2. Now for this one, let's check. If we will give W1 here and 1 here and W2 here, what we will get? What we will get here? If it is 0, then select the W1. So that means W2 dash W1, right? So here W3 dash, if it is 0, that means W3 dash. So W2, that will be reflected here. F is equal to plus, if it is W3, then the multiplexer output will be W2 dash W1. Okay, so something is there. W3 dash W2 is coming, W3 dash. No, here two outputs will be there. W2 dash W1 plus W2, right? Plus W2. Just a minute here, I'm making a mistake. Otherwise, you have to take different permutation and combination to solve this problem. So here the output will be the W2 dash W1 and plus W2. Okay, so here it is W2, W3 dash, that is correct, and W3 multiplication of, that is W2 dash W1 plus W2. So if we do that, so we will get W2 W3 dash plus W3. If we further solve it, then we will get W1 plus W2 dash. If we there is one formula is there. So if you in the starting logic functions, we will get w1 plus w2 dash. Okay, so you will get this function if you solve this. Okay, try for this one, you will get it. Okay, so our logic function, if these inputs are given in that places, we will get this logic function. Okay, so have you understand this one? Just we need to check all the input combination. Other combinations are also possible. You can check it. Okay. Okay. So I hope you have understand this question, or you can solve it by yourself. Also, you can check it once. See what combinations we can apply so that we can get the at the output this possible combinations. Okay. So moving to the next question. So next question is to guarantee correction of up to 5 errors in all cases, the minimum Hamming distance in a block code must be. So to guarantee correction up to 5 errors in all cases, the minimum Hamming distance in a block code must be. So already we know that what is a Hamming distance. So Hamming distance between two words of the same size is the number of distance between the corresponding bits. Okay. For example, it is given 0, 1, 0, 1. Here it is given 0, 1, 0, 0. So here, if you take XOR of these two bits, then you will get the mean distance. Or you can directly write where it is number of the bits are same, you can put it 0, and where it is different, you will take 1. So the number of ones is the Hamming distance. Okay, difference between the corresponding bits. So to guarantee the correction of up to errors, you can write to guarantee up to, I am taking here t errors, we can say that t error in all cases, the Hamming distance must be, it is a formula, that is d is the Hamming distance is minimum 2t plus 1 to guarantee up to t errors. Okay, so here t is given, that is 5. So to guarantee the up to t errors minimum, for minimum Hamming distance we can take as a d minimum. So d minimum, because here it is minimum Hamming distance. So t is given here, that is 5. So 2 into 5 plus 1, that is 11, right? So it will come the 11. To guarantee correction up to 5 errors in all cases, the minimum Hamming distance in a block code must be, that is 11. The minimum Hamming distance is 11. That is option 1 is correct. Okay, so this one is the formula. To guarantee up to t errors in all cases, the Hamming distance must be, that is 2d minimum must be greater than equal to 2t plus 1. Okay. So from here t already we know that here it is given up to 5 errors. So put t is equal to 5 and we will get 11. Okay. Okay. So I hope you have understand this. So moving to the next question. So next question is also related to Hamming distance. So already I have told you what is a Hamming distance. So what is the Hamming distance between the codes? That is 1, 1, 0, 0, 1, 0, 1, 1. That is 1, 0, 0, 0, 0, 1, 1, 1. Okay. So what will be the Hamming distance between these two codes? So simply we have to take XOR of these codes and then check the number of ones. Yeah, what will be the Hamming distance? 3. Yeah, 3. So 1 XOR 1 is 0 because it's same, it is also 0. Here 1, here it is also 1. 0, 0, here it is a 1, it is a 0. So number of ones are there. Number of ones is equal to 3. So Hamming distance will be 3. Distance is equal to 3. So option 2 is the correct answer for this question. Okay. So now moving to the next question. The next question is the PAL circuit programmable array logic has a and or fixed or and programmable and array programmable or fixed and or programmable and array is fixed or programmable. Yeah. And array is programmable and or array is fixed. It is a PAL. Okay, it is a PAL. Programmable array logic. There is another one, PLA. Programmable logic array. That means both are programmable. Both are programmable. Here and is programmable or is fixed. Okay, so moving to the next question. So next question is, if the computer has 32K words, then this memory unit has a memory location. If computer has a 32K words, 32K words. So already we know that 1K is equal to 1024 bytes, right? For 132 bits, for 32K, that is 32 into 1024. Okay, so if you multiply, you will get 32,768 bytes. Okay, 32. Yeah, that one is also correct. You can solve it anyway. So you can directly, so 32 means 2 to the power 5 or it is a 2 to the power 10. You can 2 to the power 15, you will get this number only. Okay, so option 1 is the correct answer for this question. Okay, so moving to the next question. So next question is, consider a memory chip with 24 address pins and 16 data pins. How many locations it will accommodate? So here address pins are 24, data pins is 16. That means 2 to the power 24 into 16, right? Data pins means 16 data pins that we have to given the data that will be input data, and 224 is the address locations where the data will be stored. Okay, it is related to the memory locations. Okay, so the here we have how many location it will accommodate. That means 2 to the power 24 locations will be there. 2 to the power 24 locations are there for data accommodation. Okay, so 2 to the power 24 is the correct answer. 2 to the power 24 locations are there for data accommodation, and date 16 are the data pins where we have to send the data. It is a not location. Okay, this represents the location where data will be stored. Okay, so that's why they have asked only for how many locations will it accommodate. Okay, so they have asked only the location, so that is 2 to the power 24. Okay, so moving to the next question. So next question is also related to this. So addressing the of the 32K into 16 memory is realized using single decoder. Here they have used the decoder. The minimum number of AND gates required for the decoder. So they have asked how many AND gates are required for the decoder. Okay, so if we solve it, it is 2 to the power 5 and k is the 2 to the power 10. Already we know that, and it is a 16, right? So if we do it, it is a 2 to the power 15 into 16. Okay, so for the decoder, already we know that in the decoder implementation, so n is to 2 to the power n. Okay, that means n data input and 2 to the power n is the output. So in the decoder, here n is the number of AND gates are required. It is a 2 to the power n is the number of AND gates required. AND gates are required. So if we compare this, that is n is equal to 15. Okay, so total how many? That is 2 to the power 15. That is, it is not 2 to the power 15 AND gates are required. Are required for decoder. Okay, so that is 2 to the power 15 is the total number if we implement using the decoder. So minimum number of AND gates required, that is 2 to the power 15. Okay, now moving to the last question, that is question number 25. So here it is given, consider a binary code that consists of only 4 valid code words, that is, it is given. These are the 4 valid code. So let the minimum Hamming distance of the code be p. So we need to find out the minimum Hamming distance, that is represented by p, and the maximum number of erroneous bit that can be corrected by the code q. It is represented by erroneous bit, that is represented by q. Then the value of p and q. So now we need to find out the Hamming distance to all, between these all. So now let's check for between code 1 and 2. So that is 0 0 0 0 0 0 1 0 1 1. So minimum Hamming distance will be 0 1 0 1 1. So here the Hamming distance is 3. I am representing as a D1. Okay. Now we need to check this one and this one. So how many minimum Hamming distance will be? D2. We can directly write it here because it is all 0. So the minimum Hamming distance will be 3 ones are there. So that is 3. For here it is a D1, D2. Here it is a D1, D3. Between D1, D3. Okay, I am representing. Between D1 and D4, this is a 1, 2, 3, 4. It is a 1, 2, 3, 4. I am representing the minimum Hamming distance. So between D1, 2, it is 3. Between the 1 and 3, this is a 3. Between 1 and 4, it is a 4. So it is a not minimum. Now check for 2, 3. The minimum Hamming distance between the 2, 3 is how many? Now 0, 1, 0, 1, 1. Okay, so 1 0 1 0 1. So 0 1 1 1 1, right? So here it is also 4. Now D2 3 D2 4. We have to check again for this one and this one. So 0 1 0 1 1 1 1 1 1 0. So 1 0 1 0 1. So minimum Hamming distance is 3. We have to make now last one is D 3 4. So it is a 1 0 1 0 1 0. So 1 1 0 1 0. So it is also 3. So if we need to take a minimum Hamming distance. If we take D minimum, this is a minimum of all, that is D12. I can remove from here. D12, D13, D14, D23, D24, D34. So it is a minimum of, that is 3 3 4 4 3 3. So the minimum is 3, so D minimum will be 3, and it is represented by P, so that means P is equal to 3. Okay, now you have understand this one. P is equal to 3 we have got. Now we need to check the next one, and the maximum number of erroneous bits that can be corrected by the code is represented by Q. That means Q. So maximum number of erroneous bit is represented by, I can write it, maximum number of erroneous bit. The formula is D minus 1 by 2. That means D minimum. So D minimum already we have got, that is 3. So 3 minus 1 divided by 2. Okay, so we will get 1. So Q is equal to 1. Q is equal to 1. So P is equal to 3 and Q is equal to 1 is the final answer for this question. So the values of P and Q are 3 and 1. That is option 1 is the correct answer for this question. Okay. So I hope all of you have understand this question. So these are the questions which have been I have covered for this week. So total 25 questions are there. Okay, so now I have completed my questions. So if you have any doubt, you can ask. Otherwise, we can close this session. Okay. So you guys don't have any question problem. Okay. So thank you everyone. Thank you for joining this session. If you have any doubt, you can now ask the question. Ask your questions. Otherwise, we can leave the session. Okay. Thank you everyone. Thank you for joining this session. Now you can leave the session if you don't have any doubt. Okay. So thank you everyone. Thank you for joining this session.